Hello, I hope everybody's still wide awake for the penultimate presentation of the day. My name is Bjorn, and I'm going to present you the work I've done with Michael Everett and John Howe at MIT, supported by Ford, and it's called Certified Adversarial Robustness for Deep Reinforcement Learning. Now, we're facing this dire situation where we build autonomous systems and we make them strongly rely on black box predictions from deep neural networks, even for safety-critical tasks, such as autonomous driving. Now, the problem is that the underlying neural networks are incredibly brittle. They can fail on small, tiny perturbations of the observations in the input space, so-called adversarial examples coined by Goodfellow. For example, a small sticker on the road has caused a real autonomous vehicle to swerve into the oncoming lane. Now, that was on a test track, so nobody got hurt, but it points out the importance of addressing the questions, how can we achieve deep neural network-based systems that are robust to these adversarial examples? So in DeepRL, we currently only have defense algorithms with empirical guarantees, for example, adversarial training, but no algorithms with theoretical guarantees. In the computer vision community, however, there's these novel, exciting certification algorithms, such as fast linear reluplex, that provide theoretical guarantees that given bounded adversarial examples, they will not change the classification decisions. So what we do is we adapt these recent breakthrough technologies of real-time certified defenses to DeepRL tasks. So in the example task of collision avoidance, our algorithm works as follows. There's an orange agent that tries to reach its goal while avoiding this blue dynamic obstacle. However, there's an adversary that has access to the true state and checks what would be the worst possible action in the given state. So here, the one that collides. And it does so it can present the agent with a corrupted observation that makes the agent choose the worst possible actions. So a standard DQN agent would only see the corrupted observation, maximize the Q value, and executes the worst possible action, here colliding. So what can we do to defend against this adversary? Well, we can trace back what was the true state, but we know it's somewhere in this epsilon ball, because that's how adversarial examples are crafted. So we take a conservative assumption, that for each action, the worst thing could happen. So in other words, we assume that for each action, the true state would minimize the Q value. And then we take the action with the best worst case outcome, avoiding a collision. Now, the worst case Q value is incredibly challenging to compute because you'd have to theoretically query your network for every single state in the epsilon ball. So we use the certified defense algorithms from the computer vision community to give us these guaranteed lower bounds on the worst case Q value. And in the end, making us certifiably robust against this adversary. We have evaluated our algorithm on simulated collision avoidance scenarios, and the algorithm dramatically reduced the number of collisions under adversarial attack. It runs as an add-on to standard DeepRL algorithms in real time, and the theory is generally enough for other RL tasks and inputs. Thank you very much. If you have questions or feel incredibly excited about this, come to me, talk to the poster, or shoot me an email. Thank you very much.